got the other one. Select box 2. Select box 2. Shoot him. I don't got cone. Got the second one. I got the second one on the nose right now. Hey, I'm high cover on you. Get a lock him up. Lock him up. Damn, shoot him. Box 2. I can't. I don't have a fucking cone. So what? Good kill. Good kill. Hey, good kill.
This is Authentic.
Welcome to the beginning of Authentic's episode on the AIM-9 missile. I'm Scott Roger Chaffee, and I'm here with Brian Sunshine Sinclair. Pardon me. How you doing, Sunshine?
Doing well, Roger. I enjoyed our little back and forth there, and I guess we could roll up our sleeves and get into it if you like.
Let's get into it, because we're here to talk about the AIM-9, better known as the Sidewinder. And I think it needs little introduction, but Brian, I'm just going to toss right over to you. Let's talk about how we got to what is very possibly today the premier within visual range infrared missile in the world.
Sure thing. And let me back up. So, I did some operational tours in the F-18, but
sure.
And I respected the AIM-9, and we flew with the AIM-9 Mike and X, and we'll get into those variants, if you will, in the discussion later. But I didn't really have the thorough appreciation or really the thorough background knowledge to fully appreciate the Sidewinder until I got my VX-31 test tour in China Lake in Ridgecrest, California. So, and that was because that is the home of the Sidewinder, right?
Okay.
And so as I learned more about Dr. William McLean, the kind of father of the Sidewinder, and the iterations it went through, it just, I kind of geeked out, I'll be honest with you, and became a very fascinating story of kind of technical ingenuity as well as operational application. All right. And I'll step through that to explain exactly what I mean by that. But there's some novel concepts that were built into this thing that hadn't been seen before. Some of them were passive designs, meaning it doesn't take electricity, doesn't take any kind of logic. It just happens naturally just by pretty much harnessing physics to do what you want to do. And we'll get into roll-arounds and we'll talk about that. But anyway, so there's a lot of just ingenuity, we'll say, that went into that. And but this program actually started with the Germans, and that's kind of lending to your point of the segue from Star Wars or really, right? So think Germany, World War II, they have their buzz bombs, right? So there's V1, V2, there are a couple other V bombs anyway, and the V I think was Vengeance, if that sounds right. But
yeah, that's correct.
Point being is they wanted to, instead of just having it fly a certain trajectory and hit whatever was available, they thought, what if we actually designated targets, heat sensing or heat sources, on the ground? What if we had a way to sense the source and then go ahead and cue the missile or really guide the missile into its target? So they had a Project Hamburg, it was called. So the German scientists there were working on an IR sensor, an IR tracker, whatever you want to call it. And we'll talk about their rudimentary design that actually was incorporated into the early Sidewinders using a spinning filter, if you will. But they went from there. They basically matured the system as much as it could be as a sensor, but they had yet to integrate it into any of their missiles or their buzz bomb, to become a missile. Right. And then the war ended. So the war ended, obviously, hooray to the Allies, right? So some of the German scientists, the high-ranking military officials, the technical officers, if you will, they had a choice: go to jail, get shot, or come over to the U.S. and help us, right? So the Allies ended up divvying up a lot of the technical expertise, right, as well as the technical files or records. And over here, do you remember we had Operation Paperclip? Yeah, so I do. Right, so we brought over Warner von Braun, I think, is a great example of Operation Paperclip, right? Bringing over rocket technology that NASA, originally NASA's going to use to help us with our space race, if you will. So besides that, though, the German engineers came over, and that Hamburg project technology, we'll call it, landed in Dr. William McLean's lap in Ridgecrest, California. Back, it was called NOTS, right? Naval Ordnance Test Station, which later becomes NAWS, Naval Air Weapons Station, China Lake. Same spot in Ridgecrest there. And he starts off with a little bit of side money kind of thing, and it's more of a side project, actually, kind of a garage project. And what he wants to do is he's hoping to take are you familiar with Zuni rockets?
I am.
Yeah. Well, it's indeed a rocket, right? So you just kind of fire it, and the ballistics are going to make it land wherever it lands, whether it be wind or whatever affects it. So now he wanted to turn a rocket into a missile, and hopefully folks at home know the difference between the two, right?
Well, I'll as usual, I'll take the layman point of view. If you guide a rocket, it turns into a missile, right?
Nailed it. That's exactly right.
Yeah.
Exactly right. So Dr. McLean was hoping to take a Zuni rocket and make it become an IR missile. And so they went through some iterations, if you will. And as it turned out, he was successful with it. And it's to the point that as he's working through this, they're trying to figure out the technology and how to integrate it into a weapon. And they, as you can imagine, they start getting more and more money because it seems to be going somewhere. And they start to get some test pilots that are going to help with the test and evaluation portion of it. And does the name Wally Schirra sound familiar at all?
Just vaguely, from something about
from
moonshots in NASA. Yeah.
There you go. Good old Mercury 7 days, right? So it turns out Wally Schirra was actually one of the Sidewinder test pilots.
I didn't know that. Okay.
Yeah. So I'm going to start attaching some years to everything, if you will, to kind of put it into perspective. So in 1946, Dr. William McLean gets the information and starts his garage project on the Sidewinder itself.
Right.
And then in 1950, they actually came up with the name Sidewinder. And Roger, do you have any idea why they called it a Sidewinder?
Well, I think I do, and you can tell me if I'm wrong, but my understanding is at the time, guidance is probably the wrong term, but I'm going to say guidance. The guidance system was such that it was an absolute command to the flap or the aileron. It either went hard left or hard right to make its corrections. So it would either go hard left, hard right, and it would sort of, what's the word, sidewind through the sky. So they named it after the snake. At least that's how I heard the story.
Yeah, that's true. It did duplicate kind of the helical fashion. So think Ridgecrest, California. We're talking California high desert, lots of wind, lots of dust, lots of heat, right? So you got the Sidewinder, you got the rattlesnakes out there, one of which is the Sidewinder, and he does his curlicue motion. So you're spot on there. The other thing is rattlesnakes, they have IR sensing organs basically on their lips, and they use that to track and to pounce on prey. So Dr. McLean was thinking, well, here's an IR weapon that's going to go pounce on something based on an IR signature. So there's a commonality there. So let's call it the Sidewinder. And so
I didn't know that last part. I knew about the rattlesnake. I didn't know the time there. That's awesome. I'll do a little editorial aside to say, so here's the difference between a test pilot and a SWO, right? A SWO says, just that sort of lefty right thing. And the test pilot goes, helical. So yeah, there we go.
Oh yeah, sorry, dude. Well, good,
funny, man. Right? Hey, that's why we're here.
No. But you know what? So in these discussions, that kind of semantics, the word choice, diction, whatever, can sometimes serve me well. But where it doesn't serve me well is at the dinner table, and I'm trying to relay a story to my girls and my wife, and they're rolling their eyes like, dude, who talks like that? You know what I'm saying? There's a fine line, and I'm still trying to find it. You know what I'm saying?
All good, man. I think we're all works in progress, especially as we, 20 plus years trying to transition to civilian life. It's never actually going to happen. But anyway, I'm sorry for the digression. Proceed.
No, this is all good. So, so kind of snapping back to the timeline. So you're looking at the early 50s. They call it Sidewinder, and then Sidewinder 1 actually in 1952, and then in 52 also they had the first live fire.
Okay.
So they launched it. I'm not sure if Wally Schirra was the pilot or not, but anyway. And then I think that was September. And then a couple days later, it was actually September 11th of 1952. The first Sidewinder shoots down the first drone over U.S. soil. So it's not, it's out of curiosity, right? They shot it out of curiosity, not out of anger. Yeah. So no combat right now. We're just doing test and evaluation, right? Developmental test and evaluation. Yeah. So the course of the next couple years out to spanning about 54, they have about 51 test launches, and they go very well, to the point that the government and basically the stakeholders say, you know what, this is a worthwhile investment. Let's go ahead and start production. So in 1955, they start production. And then in 1956, its initial operational capability, its IOC, is with the U.S. Navy, and they're going to strap it to Grumman F9Fs as well as the FJ3 Furies.
Right.
And the intent, the the concept of employment, is actually for these Navy fighters to be able to shoot down long-range bombers. So non-maneuvering, relatively slow traveling, if you will, but high altitude, right? Bombers. So just keep that in mind as we kind of progress through the target sets, starting out with something big, slow, ugly, hanging up high. And eventually we're going to get in the 9X where you can shoot it off bore sight, right? So you can shoot a guy basically off your left or right wings. So.
Worth remembering that these missiles, all missiles were originally seen as that sort of large, slow target counter. Guns were still going to be used at that point for anything maneuvering.
Yes, and you bring up a great point. So fantastic segue into the first combat experience of the Sidewinder. Remember, it's still not an AIM-9 yet. It's called the Sidewinder.
Right.
And that's going to be good old the Chinese Communist Party in mainland China are pissed off, are fighting the Chinese nationalists who are on Taiwan, which probably sounds like a lot. The tensions were all the way.
The more things change, the more they say the same. Right.
That's so true. So from the late 50s until now, there's been tension and kind of plans for the Chinese Communist Party to reunify Taiwan. So back then, though, they had actual open hostilities, if you will.
Right.
And the Chinese Communist Party, so the mainland China, we'll just call them, they had MiG-17s, whereas the nationalists had F-86s. And if you were to compare and contrast the performance of both, you're going to see that the F-86 really doesn't have a snowball's chance against the MiG-17.
Right.
So MiG-17.
Correct me if I'm wrong, the MiG-17 took all of the lessons learned from the MiG-15 fighting the F-86 in Korea, right?
Correct.
So you're up against the plane that was designed to be better than you.
Correct. That's 120% correct. Yeah. So basically now, I don't want to say freedom of navigation, but the MiG-17s have unfettered transit of the strait there. So, between Taiwan and mainland China, you've got, it used to be called the Formosa Strait. Now it's the Strait of Taiwan, whatever you want to call it. And it's a min distance, I think, was just about 100 nautical miles. So it's a narrow body of water. Anyway, these MiG-17s would just be high, fast flyers, and they go pretty much right over top of the F-86s. And the F-86s at one time only had guns, so they couldn't pitch up, shoot them, and there was nothing they could do. So the MiGs would just run high and fast and completely leave the F-86s in the dust. And all that was true, and the U.S. noticed that, and they had something called Operation Black Magic. Is there a chance you've heard of that?
I'm not familiar with Black Magic, no.
Okay. So the U.S. said, well, why don't we give the Taiwanese a little edge up, right? A little leg up, on the competition. So they brought over the Sidewinders, and it was a black project, so not well known, obviously. They integrated them onto the F-86, and then they trained the F-86 pilots on how to employ them.
Okay, I knew that. I didn't know the name was Black Magic. Okay, interesting.
Yeah. So way back time machine again. We're looking at September 24th, 1958. There are 6 or more MiG-17s flying high and fast east. So from mainland China over to Taiwan, the F-86s are below them. Well, little did they know, the F-86s are armed with these Sidewinders. So the F-86s end up losing 6 Sidewinders. They go up and they hit 4 of the MiG-17s. So splash 4 MiG-17s. The other remaining MiG-17s kind of get in dogfights, but no one else is really taken out by a missile. And then they go their separate ways. And it became this, so the Sidewinder basically was a wake-up call to the Chinese, we'll call them the Chinese communists, and it became a deterrent weapon. So I know traditionally we kind of think of deterrent weapons being a nuclear weapon of some sort, right? But back in the late 50s, the deterrent weapon was actually the Sidewinder, and it kept the MiG-17s out of Taiwanese airspace. So 6 missiles were shot, 4 aircraft were shot down. But it turned out on that first day of the first combat, the 24th of September, 1958, one of the weapons, one of the other 2 that didn't shoot down a plane actually hit a plane, but it didn't go high order, so it dudded. So it stayed embedded in the MiG-17. The MiG-17 pilot was able to successfully recover the plane and the missile back in communist China. And then they basically popped the weapon or the missile out of the plane and sent it back to Russia. And the Soviet engineers reverse engineered it. And they were, and some quotes I read about, they were absolutely stunned by the innovation of the Sidewinder missile, both in the seeker as well as the passive dynamic systems on board that we'll talk about. And they came up kind of with their shameless duplicate, if you will. They called it the K-13, but for us, the NATO designator is the AA-2 Atoll. Does
Right.
that sound familiar at all?
Absolutely. Yeah.
Yeah. So
The Soviets were, never terrific in innovation in a lot of areas, but terrific at reverse engineering.
they were, yes, they were, especially given the motivation. I know Stalin used to tell them, "Hey, you will make an exact replica of this captured American weapon, or I will kill you." So
Yeah.
the
I mean,
motivation was high.
that's motivation. Yeah.
That's definitely motivation. They weren't worried about days off or
That's right.
leave
Oh
or
man, is,
pay
is
or
Shine
anything.
going to get this promotion or am I going to get it? I don't know. Oh
They
no, I'm
just
going to
wanted
get
to live.
shot if this doesn't go well.
Exactly. So the stakes were high. We'll say that, right,
Yes.
for the
Yeah.
Russian engineers there. So, all right, cool. So basically, the inaugural combat display, we'll say, of the weapon. Actually, one of the weapons fell in enemy hands. So then they worked on the Soviets, worked on their version, the AA-2 Atoll, and it turned out to be a pretty, on their side, we'll say, a very successful weapon also. So diving back a little bit, so through this evolution, we'll talk about the 12 different variants, but over the next 3 decades, right, it's probably, just like you said earlier, Scott, it's the most influential heat-seeking missile that the U.S. has, and consequently the Eastern Bloc or Soviet Union countries have too. For us, there were about 110,000 Sidewinders that were produced during those 3 decades, those 3 years.
Wow.
And they were used by the U.S. as well as 27 partner nations. And so, so it was definitely a success story. And then, if you don't mind, we'll jump back into the timeline. So we talked about 1958, right, and the Chinese communists there getting scared, if you will. And then from there, in 1965, so it was also the year that we joined Vietnam, right?
Right.
But the Sidewinder missile program was renamed to the AIM-9. So basically, from 46 when it started until 65, it was called the Sidewinder, and then it became the AIM-9. So you got the AIM-9, and then they started working on variants. The next instance of being shot in anger or combat application, combat ops, is going to be India versus Pakistan, and they're fighting over Kashmir, right, which is heavily contested environment. Yeah,
the more things change.
Yeah, exactly, yes, yeah. And so this time we backed the Pakistanis, and they had F-104s, so we put AIM-9s on the 104s, and they enjoyed a very nice success rate, we'll say, and we call it P sub K, so probability of kill.
Right.
So yeah, so the P sub K was pretty high for that. And that would be 65. And at the same time, so Vietnam, the war started in 1955, but the U.S. joined, if you will, in 1965, right? So about 10 years later into it.
Yeah.
And then we started using the AIM-9s on our aircraft, predominantly our F-4s, right, our Phantoms.
Right.
It was enjoyed by the Air Force and the Navy. Unfortunately, though, the results were less than stellar. So they looked at, and it's hard to catch numbers, especially in combat, because it's just the reporting is very difficult, as you could imagine.
Sure.
But they took a snapshot from 1965 to 1968. They had launched 452 Sidewinders, and the U.S. Navy enjoyed 46 downed aircraft, and the Air Force enjoyed 34 downed aircraft. So in other words, shooting down bad guy aircraft, right?
Right.
And so when you look at that little number over a big number, that's a ratio, that's going to be your probability of kill. It turns out long test pod answer. The probability of kill in Vietnam was about 16 to 18%.
Right.
So it's kind of in the
Which is not super.
No, not super at all. Not super at all. So they decided, hey, let's try some different variants of this. Besides an IR seeker, what if we went like with the Charlie, the AIM-9 Charlie? We'll use a radar variant. We'll see how we can mix it up. So there was a lot of tinkering, if you will. And then the next major combat action was 1982, and that would be the Falklands War. Does that kind of sound familiar? Remember who was fighting there?
That would be, well, I mean, you said the Falklands. I may consider it the Malvinas, but in which case it would be Argentina fighting Great Britain. But for the Falklands, it's Great Britain fighting Argentina.
There you go. Well played. I like that. Yeah. Well played indeed. Yeah, so the Brits had their Harriers, right, the Sea Harriers. And then we strapped AIM-9s, or really they strapped AIM-9s to them, and they ended up shooting down a whole bunch of Argentinian super, pardon my accent here, super Intendar, so the Super E, the French fighter, right, as well, or more of an attack, I guess, as well as the Skyhawks. So the Argentinians had the A4 Skyhawk, and they had the Super E. So, and the P sub K, the probability of kill, went from, in Vietnam, about 16, 18%, went up to 82%. So much, much better. So like, oh, okay, hold on.
Yeah.
So, the missile that was kind of looking like a good idea, and then Vietnam proved it otherwise, and now the Falklands are saying, hey, this actually is a very viable weapon.
Mm-hmm.
And so that was in 82. And then let's see, most recently, most folks probably remember in 2017. Do you remember there was unfortunately, it was an air-to-air miss initially, but a lieutenant by a U.S. Navy lieutenant commander, actually. I think it was Mob as his call sign. And he tried to shoot down a fitter, an Syrian Su-22
Right.
fitter. Yeah, so he used an AIM-9. I think it was AIM-9X because he was in theater. And unfortunately, it was decoyed by the flares, the Soviet flares. So then he consummated the the intercept with an AIM-120.
Right.
Yeah.
So as we look back at this, and if you want to talk about this in a different tangent or a different phase, that's fine, but we can do it now. So, we see some early, I think, obviously the Taiwanese and the Chinese, there's an element of surprise. And usually any weapon that is technically viable works really well when you have that first element of surprise. And then the Pakistanis do well against the Indians, especially, coming from a fighter that's not generally considered a great dogfighter, right? The F-104, real fast in a straight line. Yeah, exactly. Doesn't turn super well.
No.
And then we have, a sort of horrible experience in Vietnam with that and with the Sparrow. And then the Brits come back. So how much of that is variant? How much of that is training? How much of that is circumstance? And by circumstance or training, so for example, I was talking in another interview with an early model F-16 pilot, and you may get to this, but I did not realize that there were essentially two seeker tones. And you can hear that in our intro to the show earlier with some audio provided by Sunshine. Sure. I didn't realize there were two seeker tones. One that said, the missile says, I see the target. And then the missile says, well, I have enough to now lock onto the target. So what changed? Was it technology? Was it training? Was it all of it?
It's a calculus problem, so it's a little bit of everything, if you will. But you know what? Something I forgot in history, but I'm so glad you mentioned the tone, is when Wally Schirra, when they were still doing the developmental test, that seeker indication originally was merely a voltage gauge in the cockpit. So in other words, so just like you said, we have a two-tone, like a tone rise showing a missile or seeker lock, really. So back then, they'd be maneuvering, as you can imagine. This is an altitude, airspeed, and G-dependent weapon, right? So only so many G's, so high. Anyway, so Wally Schirra is doing some maneuvering with the weapon in developmental tests, with the aircraft in developmental tests, And to actually verify seeker lock-on, he has to bring his scan out of the cockpit back into a little gauge and make sure the gauge needle has moved to show that there's seeker lock-on.
Yeah.
And so in a lot of their post-flight reports, they said, hey, it's got good performance at this airspeed altitude G regime, we'll call it. But, one of the real annoyances, and that could actually cause a mission failure, is I have to take my eyes off the target, which is never good in dogfighting, right? Bring them inside, stare at this little gauge, analyze the gauge needle deflection, if you will, and then come back outside. Anyway, so that was a definite other in the design. So they said, hey, I got an idea. What if instead of having to look at a gauge, what if we use a tone?
Yeah.
And so to your point, so they got this tone, and it's 840 hertz, whatever. Anyway, it's a lower growl, we call it, right? And then it's going to escalate very easily, and it's very discernible, the tone rise for when it's locked on. So having tone rise, as well as knowing how to effectively employ the weapon, that would be tactics, right? And the tactics we're developing, but as you can imagine, I don't know about the Pakistani Air Force there, but the Brits, they're great chaps, but it was a relatively new weapon. I think it was introduced during the Falklands War. So
that particular model of Sidewinder.
So there's not a lot of training to do before you employ it, but it still had a lot of great success versus Vietnam. The technology was slightly different. So, and when we get into the components, we'll talk about the differences, but imagine a seeker being not as sensitive and easily fooled. So if it's heat seeking and my target flies into the path of the sun, right, then I'm going to lose it. Or as you know, with IR, within kind of infrared emissions, if you fly into visible moisture, so clouds, you can diffuse that, right? So there's ways to foil it. And then there's also flares. So as the technology evolved, so did the tactics, as you could imagine. So the kind of the employment envelope got more robust as the detector got more sensitive, as well as the weapon got more maneuverable, right? So long test pilot answer again, sorry, but as basically you have this confluence of all the tech increasing as well as the tactics increasing or getting better.
Right.
And then you're going to see more results that you have today.
So the arrow's getting better, the archer's getting better.
Yeah.
It's, and you know, all the
Spot
way
on.
around. Okay.
Spot on.
Awesome.
That's exactly right. Yeah.
Awesome.
So Mob, yeah. So Mob, and it's no error on Mob's part. So Lieutenant Commander Tremmel, right? The guy who shot at the fitter, the Su-22, the Syrian plane. But it's merely the missile, and it was well documented via combat footage. It missed and locked on, basically was decoyed or pulled away from the target by flares.
Right.
So nothing against him. So that was in 2017. And then most recently, as in this year, 2023, right? We had a couple AIM-9 shoot down some high slow flyers.
That's right.
You know what I mean? So do you remember any of those?
I do. In fact, not to too blatantly advertise, you can go back on Authentic and we talked to Scar Van Timmerman about the shoot downs.
Yes.
But let's talk about, just briefly again, recap. It was sort of one of the best choices for that mission, for the balloon mission.
It was. They had actually some of the I'm careful what I say here. So
of course,
So here you go. Okay, so I'm just going to state facts that don't lead to capabilities or tactics. Absolutely. So I think it was the late 90s. The Canadians had a weather balloon, an errant weather balloon over kind of Western Canada somewhere, got into the jet stream, and then it trundled east. Well, the Canadians didn't want this floating hazard that's moving, right? So they wanted to shoot it down. So they actually launched a Canadian F-18 with a bunch of bullets in its nose and said, go shoot this thing down. Well, do you know how successful it was?
I can't quantify it other than to say not.
Exactly. Yeah. Yes. That's exactly right. Yeah. So anyway, it took several days, if not an entire week from the engagement where he hit his target multiple times until it actually deflated. Because the holes were so small, as you can imagine, it was kind of inconsequential. The lighter than air gas stayed in the container, and up it stayed. So anyway, so when they're assessing how to take down these weird balloons, we'll call them over the U.S., they had lessons learned from the Canadians. They said, well, shooting doesn't go well. Plus, let's say, so you got 578 rounds in the nose, right, for the typical Rhino loadout. Even if they go through the balloon, they're not going to stop in the balloon somewhere, right? So chances are you're probably going to have almost 550 at least rounds continue downrange and land somewhere, right? So you got basically a hazard pattern that's pretty darn big. Yeah. So they decided to go with the AIM-9. So anyway, the only one that was the first one, I guess, really, that was shot down off the coast of South Carolina, right? And kind of as the episode of which they spoke, it was impressive because that balloon was up at 60 to 65,000 feet, and so, to my knowledge, that was I call it envelope expansion. So I'm not sure that we'd ever try to shoot down a target up at that altitude before. And so the F-22, very capable aircraft, obviously had to climb high fast to get up. It didn't get up next to it, obviously, but it got up high enough that it was in range, if you will, for the AIM-9. So very impressive that it took it out. And then and we'll get into, I guess, the warhead and how that worked and all that stuff. But it has this continuous rod warhead. Or I'm sorry, the AIM-9X actually has an annular explosion, right?
Oh, okay. Yeah.
Sorry about that. So,
no, all good. I mean, they evolved continuous rod, and they may have even changed SM2s, but that's, I'm familiar with continuous rod from SM2.
Yes. Okay. Yeah. Totally. So, so that's kind of the history, I guess you could say, of the air to air, and then they also looked at air to ground. So they looked at using the AIM-9 as an AGM missile, also, right? So attacking surface targets, and that a lot of that effort for testing was done at China Lake. And I was there. I flew around with a CATM to try to detect. They call it delta T, right? So basically a thermal difference between the background and the target. That way the sensor can discern the target, if you will. Anyway, so I flew some flights with a CATM, but I never got to shoot anything with an AIM-9 on the ground during test. I did shoot it in the fleet. I got to shoot a paraflare. We'll talk about.
Nice.
But anyway, yeah. So And then besides the air to ground capability for the Navy, which hasn't been fully vetted or is operational, but also the Army actually mounted some AIM-9s on a multi-mission launcher. I think it's called the MML. So it's a mobile kind of tank looking thing anyway. And they've got good success with shooting down drones and I think cruise missiles.
Yeah.
With the MML based Sidewinders.
If it's the one I'm thinking of, it looks like a little quad launcher, right? Like
exactly
rail.
Right. Yep.
Yeah.
Yes.
Yep.
Yeah,
they could put it.
Yep.
I think I've seen it on a track chassis, and I think I've even seen it on a trailer, but that may have been a concept.
Oh, okay, cool.
Thing.
I've only seen the track chassis, yeah. So, but the trailer makes sense too. So, so what did we say? Is that kind of we'll say the IOC back in '56? Here's public math about to now. You're looking at actually the AIM-9 Block 2 came about in I think the early 2000s. So you're looking at about 50-ish years, we'll say, right?
Yeah.
And during that time, we had, I think it was 12 different variants of the AIM-9. So predominantly they're infrared seeking, if you will, so IR, right, missiles. The C was a radar version, radar guided, version that it was okay, you know what I'm saying, but they went back to
didn't
the
really
IR.
pan out anywhere, yeah.
Yeah, exactly right. And some of that, and it was semi-active radar. So in other words, the aircraft had to illuminate the target with its onboard, it's organic.
Got to keep pointing at the target.
Yep, exactly. Kind of like the mechanics of the AIM-7, the Sparrow, right?
Works for us in a surface ship, not so great in a fighter plane.
There you go, exactly right. Now, the problem is, as you can imagine, Scott, if the target has raw gear, then he's more aware. Somebody's illuminated him, so somebody's painted him and they're going to shoot him, right? Whereas IR is passive, so it's harder to detect.
If you don't see it or don't have some other cue, you don't know it's coming.
Exactly, yeah.
Can't evade what you don't know is there.
Exactly. And then, and we'll eventually end up on the AIM-9X, which is the weapon of choice these days. Obviously, they had the Block 2 and the Block 3, and the Block 3 was canceled. It was originally envisioned to be on the F-35. They were going to put, I think, 6 of them on an F-35 to do some good work. And then they actually cut down or cut back, I guess, the purchase orders the Navy did for the the DOD did for the F-35. And as a result, they said, well, we don't need as many missiles after all. So they canceled the Block 3 AIM-9X program. So,
okay.
Yeah. So I kind of feel that is hopefully start to present, we'll say anyway.
Start to present. I mean, we started with the Chinese. We ended with the Chinese, I guess you could say.
That's true with the Chinese balloons.
I'll be hearing from the State Department at some point, I know. Wouldn't be the first time. Don't want to talk about it. But
exactly. Yeah.
So that's the history of the missile, very concisely yet informatively. So thank you for that. But let's start talking about these component parts, like you were saying, because there's a lot to it. Now, I think everyone thinks about infrared missile and they think, that homing system is the first infrared, but there's so much more than that, as you alluded to, that was revolutionary in this missile.
Yeah, there really was. And I would almost offer up that I think of this thing as a kamikaze robot. So bear with me in that I'm thinking kamikaze, obviously it's going to hit her. Really, it's got a proximity fuse, so it's get close to the target, then it explodes. But also the robotics, so the sensor to the guidance and control, all the way to the terminal logic and the proximity fuse. It's a very elegant solution. And just at the time, back in the 40s and 50s, it was avant-garde, it was novel, it was beyond his time. I'll say that. So anyway, so if you don't mind, we'll just step into it.
Yeah, let's step into it. I'll say you mentioned it being elegant. And I know, people, friends, family, all different interests, walks of life, political views on life. And a lot of people go, how do you find a weapon elegant? How do you find this missile elegant? But, no one bats an eye if you say a samurai sword is elegant, right? And I think there's that intellectual separation because of time, but this really is, if you simply accept that there's a need for weapons like this, and if you don't, then it's a whole different discussion. But if you do, it's an elegant solution because it's really got everything it needs and nothing it doesn't.
Yes, absolutely. And then hand in hand with elegance, I think of efficiency, but put in a pretty package. Yeah. So efficiency meaning input, or really output. It's a rate. I'm sorry, engineer again here. It's an output over input, right? Is the ratio for efficiency, and the amount of input required. So that would be the air crew effort, put in to shoot this weapon, and then the output being to schwack the target.
Yep.
It's very efficient. I'll say that. So
Yeah.
it doesn't take a lot of training, which
Mm-hmm.
is fantastic. It's got a lot of intuitive cues to it, as well as it's got a very forgiving or robust performance envelope. So it's for lack of a better term, it's an easy weapon to use.
Yeah.
And it's cool. So I call it an elegant solution.
I like it.
Yeah.
All right, let's take a deeper look.
Okay, cool. So looking at the slides, so stop looking at my ugly mug and we'll check out on the slides here. As you're going to see, so here's the AIM-9. All right, this is not an AIM-9X. This is somewhere in the, we'll call mid-generation.
Sure.
So starting from apparent left to right here, we got the seeker, and we'll step through the cone and the mirrors and the filter, and then we'll talk about how all that input, the sensor input, is used for guidance. All right, that's going to be basically how does the weapon think to intercept, if you will. And then we'll talk about when it gets close enough, it's going to go through target detection. And we'll talk about how the target detector works. Warhead itself is pretty cool. We alluded to it earlier. There's two flavors. There's the continuous rod as well as annular explosion, right? And then you notice the yellow band there. Does that look familiar at all from your Navy?
That's live ordnance. Live
Yeah, exactly
HE.
right.
Yeah.
Yeah, HE, exactly. High explosives. You got high explosive in the front, and then it may be hard to see in this graphic here, but this is a brown band, meaning it's got a live rocket motor.
Right.
So still ordnance, but more directed ordnance, we'll say, as opposed to the HE yellow band in the front.
Right.
So we'll talk a little about the rocket motor. Yeah, that's how it hangs on the aircraft. The hangar's not too worried about. And then in the wings, you got the stability vanes in the back. Rollerons. If you don't mind, we're going to anchor on that, and I'm going to geek out because the rollerons, they're passive. And when you talk about elegant, this is actually a really way cool way, if that makes sense, to stabilize the missile in flight.
Okay. Yeah, let's hear about it.
Okay. All right. So we'll move on here. So we'll move on to we'll start with the seeker. So the seeker, the actual dome itself, it's there's many different composites and or different materials, excuse me. And this is where I have to kind of throttle back on the details, if you will, because yeah, it's not for public consumption all the time.
We don't need visits from guys in suits.
Yeah, men in black, exactly right. So, but what I can tell you is it's twofold. This dome, excuse me. One, as you could imagine, is to protect it protect the sensor aerodynamically. So from just kind of the blunt force of we call it the ram, right? Basically the effects of air smashing into it.
Sure.
But it also acts as a filter, so it can filter out some wavelengths.
Okay.
All right. So what you're going to have here, you're going to see is if something is high intensity heat wise, it tends to have a higher frequency emission. So not a brighter, but actually the color of the flame coming out, we'll call it in basic terms here, is going to be a little like a brighter blue as opposed to a deep red. So if you think of the visible spectrum, right, we'll think high energy blue, lower energy red.
Right.
So afterburn.
Let me just interrupt real quick for the man on the street analogy and tell me if I'm wrong. But if you light a match, right?
Yeah.
And you look at the composition of the flame, it's hottest near combustion. It's hottest near the tip of the match. It's blue. And as the flame goes up, it becomes progressively more pale yellow orange. Same concept, right? Okay.
Spot on. That's exactly right. So the old Roy G. Biv of the rainbow.
Roy G. Biv. There we go.
Yeah. The V is going to be the high energy, which turns out to be high frequency, short wavelength. And then the R, the other end of the spectrum, is kind of lower energy. So so a person would give off body heat is going to be more in the red version or red region, I guess. And then afterburning plume of a jet aircraft is going to be more in the blue version in this analogy.
Right. The wavelengths. Yeah.
Yeah. The higher energy.
The frequencies. Yeah.
Yeah. So it's not quite blue, but we're trying to relate it to the visible spectrum. Anyway, so what happens is this protects it from air loads, right? The sensor from air loads, the cap or dome, as well as it acts as a filter for lower energy stuff. So it can help to remove some of the non-afterburning plumes or signatures from the ground or the sun and all that stuff. So it's kind of cool that way. So you got that. And then inside of the dome here is, bear with me, they call it a Cassegrain mirror system. Have you, if you think of a reflector telescope where they have a parabolic mirror and then a concave mirror and then a convex mirror, convex mirror bigger, concave mirror small. Yeah, it's the same kind of setup. So here what we'll do is we're going to dive into the inside. So a lot of stuff here. Bear with me. Let's look over on the left-hand side. All right. Hopefully you can see my little spinning laser dot there, right? Okay, cool. So you got the dome that we talked about earlier. That's from the picture. That's going to be this beast right here.
Mm-hmm.
And then on the inside of the dome is going to be this Cassegrain mirror thing. So what it is the light actually kind of bends on itself. So it effectively takes a longer focal length, which is required, and shrinks it inside the missile because the light's bouncing around.
Right.
So what you have is a convex, right? Kind of a cave, or concave, excuse me, a concave kind of lens right here. And so the initial rays come in, they hit this bigger curved mirror, they bounce up to, it's supposed to be technically a convex mirror here, excuse me, and then it's focused through a reticle that we'll talk about shortly. Mm-hmm. And then from there, it's enhanced, if you will, and then it hits the detector. So that's how the seeker works. Now, the seeker, though, is, and this tech is actually back from the Germans in World War II. It's been streamlined or made more efficient, if you will, but it's basically rudimentary German World War II technology. And so, Scott, do you see this kind of looks like the Japanese flag, like the rising sun thing right here? Yeah. So what happens is, this guy spins pretty quickly in front of the detector right here at the reticle. And what happens is, as it sees the light, think of it like as it sees the light and it's spinning, if the light source where my laser dot is somewhere on the outside of the disc, it's actually brighter. It's perceived as brighter by the detector as opposed to somewhere if it's in closer.
Okay. No, that makes sense. And that's because of the mirror array you just described, right?
Almost. It's actually because what happens here is wherever you see a black stripe, that absorbs the light, so it's opaque. And then where it's white, it's going to be translucent. So it's going to let light through. So, so bear with me. This is trying to take linear and turn it into circular. But if you think of your blinds at home, so plantation shutters or blinds, whatever, or shutters, excuse me, where you can move. If it's too bright, the sun's right in your face, you kind of move all the slats.
Yeah,
you can open them up,
the Venetian blinds, and you just rotate it up, down, completely closed, whatever you need.
Exactly. So think of Venetian blinds, and then they're going to actually orient them in a circular fashion. So full open Venetian blind is out here, whereas almost completely closed is in here.
I see. I gotcha. Okay.
Now this guy is going to spin. So what's going to happen is this is also translucent. So it lets light through this gray part here. But it's basically as this thing spins, if the dot's closer to the open Venetian blinds, we'll say, it lets more light through and the intensity is greater as detected by the sensor. So what that tells me, sorry.
No, I just said,
Yeah, fair.
Oh,
sorry. So then what happens is if the light source is closer to in here, those Venetian blinds are more closed so that it lets less light through and it's less intense.
Okay.
So that difference in intensity can actually, through some math and all that stuff, can help the sensor to figure out where it is radially, if that makes sense. So whether it's kind of toward the middle of the sensor or if it's toward the outside is going to be based on.
Where is it on that line that's going up the sunbeam, so to speak?
Yes. Yeah, exactly right. So that's amplitude. So they call it amplitude. To me, to the two of us, it would be intensity. But basically, a bright source is going to be toward the edge of the reticle, and a dim source is going to be toward the middle. So if it's brighter, it has to move toward it to help has to aim toward it, the whole reticle and the missile, because the end state is you want to be have it in the middle, basically, where there'd be very little source or very little intensity.
Okay.
Wow. Okay. So thank you for bearing with me on that one. So
all good.
That's amplitude. Now, if you were to take that same kind of rising sun and you make it all spokes, and then you have it kind of off kilter, so it spins not about the center, but actually spins about this point here where my laser dot is. What happens now is you get the intensity variation, sure, but you also get the rate of change from a blind open to a blind close, right? Is going to vary too. And what happens is now the frequency of the kind of the pulsating of that source will also change. And then you can do some math and it can figure out where it is in relation to the center based on the frequency as opposed to just the intensity.
Okay. No, I'm tracking with you. So, and let me know if I'm getting ahead, but essentially what's happening is in an era before, solid state electronics, right? Because I think we're still predating solid state.
Solid. Yes, you're correct. Spot on.
Yeah. This is a way for the light to drive a simple computation, or I shouldn't say light. It's infrared. It's intensity. intensity
Yeah.
to physically drive, and you'll get into this in a minute, but you sort of alluded to it. The missile guidance system is going to be hardwired to drive that source to the center.
Correct.
Right.
Correct.
And that's what this is doing here. It's saying, what's my intensity? What's my frequency? Okay, it's here on my reticle. It's here on this diagram you're showing me of the reticle. This is going on in the missile brain. And so then the missile has this simple computation of, okay, turn towards that. At least in the early stages, right?
Exactly.
Okay.
Yes, you are 120% correct. That is exactly right. Yeah. So
right.
the
outside got it, so we're good.
We're good. Yes. But you're right. And then, so this is all reticle seeker stuff. So this is the 1940s all the way to the early 80s. And then they're going to switch over to the CCD or focal plane array or charge coupled device, whatever, basically a camera.
Right.
It's going to turn into an imaging infrared camera, which is different. But I wanted to talk about the World War II tech that survived in the AIM-9 and helped it to be such a great missile all the way until the 90s.
Right.
Really,
and honestly, and then that's important because all of the counters to it were designed to defeat this. So it resets the whole game when we change that. But we'll get there, I imagine.
Yeah, you're right. And what will happen is, so it started out, they just used this amplitude modulation. So basically this disc you see here. And it's going to be almost like a cat and mouse game, right? So the air-to-air missile technology arrives, and then the enemy has countermeasures, and then the good guys have countermeasures or increase their missile sensitivity. And so it's this back and forth, if you will. So the initial cat, we'll call it in that analogy, is going to be this guy. And then you're right. They came up with flares or tactics, drive them into the clouds, drive them into the sun, try to drive them down low at thermal crossover when the Earth is very warm, we'll call it.
Right.
Anyway, and so then they said, well, shoot, now they're starting to foil our AM, amplitude modulation seeker. So now let's dial it up, right? Let's add in a little variation. Let's try a frequency modulation. And that's going to require a whole different series of countermeasures. And, I'll probably put you to sleep with that, but you get the idea of the evolution of the seeker, right?
Right. And so I think it's great that, amplitude and frequency modulation. And I think, it's not a direct analogy, but anyone who's done a cross-country drive, right?
Yeah.
If you've done it, let's say you've driven cross-country in the 80s, the late 90s, 2000s, and then maybe present day, right? So I think there's a direct parallel here in Sidewinder development of, at one point you're driving through the wide swath of Texas, let's say, and it's just, you're only getting AM reception, right? And we all know what that sounds like. And then as technology progresses, the area increases where you can get FM reception, and you just get a better clarity, you get a better signal strength and everything. And the tech is not at all parallel, but now we're listening to satellite radio, and it's that same sort of progression from the amplitude modulation to the frequency modulation to the modern day, which has nothing to do with satellites. I was just using that as an analogy, but this is what we're doing. You're just getting better fidelity in what the missile sees.
You are 120% correct once again. So great summary, and I like the analogy of the AM to FM to XM, really, right?
Yep, there you go. Yeah, I like that.
The discrete data, if you will. So
yeah,
cool. All right, so that's the seeker. So that's the eyeball and how it works. It's looking for intensity to show a radial distance, and then it can discern, I guess we'll say, an angular determination. So if it has an angle and has a radius, then it knows where it is, and they can tell the missile to go get it, right?
Yeah.
All right, cool. Now that's the seeker. Now attached behind the seeker, or the eye, is going to be the brain, right, of how the missile actually reacts. And so does proportional navigation way back when, does that sound familiar from your SWO days? ProNav?
Proportional navigation. Well, we would call it, I think, relative motion.
Yeah. How about CBDR? Does that sound familiar?
CBDR is, yes, and not in a good way.
Yes, exactly.
CBDR, okay, married guys out there, CBDR is the nautical equivalent of fine. You never want to hear it.
You never. That's true.
Yeah.
How are you, honey? I'm fine. Oh,
I'm fine.
What I do?
Oof.
What did I do? Yeah.
CBDR, constant bearing, decreasing range. If you don't mind, I'll give my quick layman analogy is when you're cruising down the freeway in the right lane and you're doing whatever speed you're doing, and you see the guy coming down the sweeping on ramp, and he's
yeah,
not
that's good.
changing where he is relative to where you're looking at him, and you're like,
Yep.
one of us is going to have to move. I have to speed up. I have to slow down. You have to speed up. You have to slow down. I have to change lanes. That's CBDR. But you know, when he starts pulling ahead of your sight line on the ramp, not ahead of you necessarily, but ahead of your sight line or falling behind your sight line, you're no longer CBDR.
Yes. Oh, that's awesome. So, and in aviator or fighter terms, I guess we're going to call it track crossing rate.
Okay.
Right. So basically you're right. It's going to be the angular difference from straight off your nose until where you perceive the guy. So if we're flying, it's 12 o'clock and we see the guy at our 9 o'clock, that's like a 90-degree, right? Track crossing. And then as he slimes forward to the 10 o'clock and then the 11 o'clock position, that's a forward moving track crossing rate. And chances are we're actually going to fall in behind him, right? Hopefully not hit him. But if he were to stay stationary, like you said, at the 10 o'clock position, this is back to your highway entrance ramp analogy, which is awesome. If he stays at 10 o'clock and we maintain our courses, we're going to run into each other. You're absolutely right, because he's merging onto me, or into my lane, excuse me. So what the missile wants to do is, believe it or not, it actually wants CBDR.
Right.
And you could imagine the angle that it's going to look for is going to be based on the relative speed difference between the target, which it probably doesn't know because it's passive, right? And the missile itself. Now, these missiles, and sorry I didn't mention this in the beginning, but these things are going Mach 2.5, or at least greater than Mach 2. And the target is, on a good day, downhill, afterburner, full grunt, whatever, is going probably 1.5 Mach at the most, right?
Right.
So it's running this thing down. But instead of just getting behind it and then trying to run over it, it wants to use the geometry. And this is what they teach us in flight school, is just, it's not always about brute force. It's not always about just selecting afterburner and trying to run the guy down. Use the natural geometry, right, to rendezvous onto the target.
Right.
And so in this case, what you can see here, and I know it's a graphic from my my old flight school days, believe it or not, but you can see aircraft A here is actually, we're going to call that the missile. And then aircraft B here will be the target. So you're going to fire, and this missile is going to perceive this certain angular displacement, if you will, from target A to its bore site, right? And then it's going to, I'm sorry, they're both called A and B. My apologies. So the blue plane is the missile, excuse me, and the red plane is the target. Sorry about that.
Right.
And basically the missile wants to maintain the same constant bearing. And if it can do that, it'll know it'll hit the guy.
Right.
So it'll consummate the intercept. Yeah. So, and then what'll happen is this ProNav, proportional navigation, is a series of control laws that's actually the sensor's going to measure the track crossing rate. So that would be the amount of motion that guy moves, like from the 9 o'clock to the 10 o'clock, or the 10 o'clock back to the 8 o'clock, whatever. And it's going to move its flight path by a certain multiplier. They call it the navigation gain. So basically but it only cares about, if it's constant bearing, the missile is not going to move its flight path. But if the guy starts to move forward, in my case on the windscreen, or aft on the windscreen, that's a rate of change. Now I need to change my flight path to adjust appropriately to maintain the same constant bearing. Yeah. So anyway, so that's proportional nav. And that's a very, once again, elegant solution, because you're not only using the delta in speed, right? Because you could just run this guy down, but instead if the guy's maneuvering, then you're going to use the angular geometry, the 3D angular geometry, to merge with the target.
Right. So instead of having to do all these computations like a radar missile might, right?
Yes.
By using my speed, my altitude, his altitude, his maneuvering, the simplicity, the elegance of the AIM-9, especially in the early versions, is I'm pointed at him and I'm still pointed at him. Sweet. I'm pointed at him. Oh, he's falling off to the right. I move right till he's no longer falling off to the right, or vice versa if it's to the left. Yep.
That's exactly right. Yeah, and the missile pulls lead, almost like a quarterback throwing to a running back who's running left to right. You got to pull some lead, right? So that's exactly right. Yeah, cool. So that's the guidance. That's ProNav. All right, now coming to the warhead. So we talked about the continuous rod, and we talked about the annular explosion, kind of like a ring of fire. Anyway, the continuous rod was around for a long time, and most of the generations of Sidewinders are that. But dude, it was hard for me to wrap my brain around this. So here, if you could draw your attention to the lower left-hand corner, when it's sitting on the missile, on the missile itself, it's a bunch of rods that are kind of welded at the ends, kind of like, I don't know, pixie sticks or what do you want to call them, but they're all wrapped together, kind of squished together very compactly. And then, so what you see here is what's down here in gray is represented by this simulation here in black. And then they're going to detonate that thing. So as they detonate it, you can imagine it's going to expand outward. It's going to blow outward. So what you're going to get is some shrapnel, obviously, as pieces fly off. You're going to get some pressure or shock waves, really, right? So it's got shock waves, which is just the change in pressure, which can really ruin a guy's day, as well as you have the heat, as well as you have these pieces of metal that continue to expand and continue to expand. So the blast radius or the fragmentation radius is much, much bigger than the radius of the actual missile itself.
Right.
So
yeah, exactly the same concept on the SM-2, and it's there's a lot of tech behind it, and why my recollection going back to that, the continuous rod is actually very simple to produce for a lot of machining reasons. But it also almost creates a knife blade, right? 'Cause the idea here was not just shrapnel. The idea was to physically try and cut through, almost, knife blade through a wing and control surface part of the fuselage.
That spot on. That's exactly right, man. This is good stuff here. Yeah. So you have the kinematics of the pressure change, as well as the energetics of the metal itself as it cuts. So, and it's got a velocity. So basically it explodes. I saw somewhere that it was like 3,000 feet per second. These rods are running ahead of the missile, right? So the missile's already going Mach 2, whatever. And then now you explode something at Mach 2, and the relative velocity has increased even more as it shreds basically the target.
Right. And so, I think that's about the same on the SM-2. So I'm going to assume that the philosophy is the same, which is, you're talking about closing on a target, as you said, at a very rapid rate.
Yes.
And so your sensors don't want to just say, okay, I've reached the target. And because for those listening and can't see it, you'll be able to go to the website and see the diagrams. But as you're looking at these, your warhead is not exploding forward precisely. It's expanding radially.
Yes.
So you want to be somewhat, if you don't directly hit your target, you want to be off to the side of your target. But to that point, the missile can't see off to its side. So it wants a fuse. It wants a fusing system that still has a little bit of ability, at least in the missiles I'm familiar with, to really have that last moment of contact and go, I know the target's there. So it throws it slightly ahead as well as expanding. At least that's what I learned at Dahlgren.
Yeah, I agree. Totally agree with you and the fellows at Dahlgren there. So I kind of think of it like a death donut. It's a high-speed death donut, right? That's going to emerge, we'll say, from the weapon itself. So the weapon itself is, let's say, has a 3 centimeter, maybe, 3 to 5 inch diameter,
Right.
But you don't have to hit it. There's no contact with the target. There's just gets in proximity, and then the death donut gets much, much bigger. So it's much more lethal, or the contact is much more robust with the target. So,
Yep.
And then, okay, you talked about fusing. So this thing is not designed to hit the target. It's designed to explode next to the target. And the way it does that is it has 8 on the, let's see, well, you can't see it in this picture, but basically for the listeners at home, behind the continuous rod warhead package are going to be some laser emitting diodes. 8 of them, it turns out. So 8 that are strung evenly around the circumference of the weapon itself, and they're facing forward, surprise. And then right next to those 8 laser emitting diodes are 8 laser sensors. And so, as you can imagine, it's kind of like having a dim flashlight in the dark. So you walk around, your dim flashlight's out, but you're not seeing anything in front of you. And then when it finally senses reflection, it detonates. So when you get close to a wall and you finally illuminate the wall, you stop.
Same concept, right? It's
same
it's
concept.
not bright enough. It's going to detect anything unless it's within a warhead, kill radius.
Exactly. Yeah. So as long, and it's you're right. So the fuse, the proximity fuse, is tuned, we'll call it, to the kill radius of the death donut. If that makes sense. Yeah. So
which again, a very elegant solution, especially for the time, because we have other missiles that have all sorts of active radar homing in their head and timing calculation. And all of this is such elegant simplicity, right? Again,
Yeah,
it's left of me, it's right of me. Go left, go right until it's not anymore. I get no reflection, I get no reflection, reflection, explode.
exactly. It's very
Yeah.
binary. Yeah. So,
Mm-hmm.
and this weapon kind of adheres to what I call Occam's, not what everyone I guess calls Occam's razor. So
Mm-hmm.
if there are many options or many avenues of approach,
Right.
the most simple one is probably the best.
Yep. Absolutely.
So I think that's what you'll see here. Yeah. So okay. So we got the death donut, we got the laser sensors, if you will, right, for the proximity, and then the roller-on. So we've moved from the front, the tip, if you will, to kind of the midsection. That was the warhead, and then the rocket motor. Sorry. So rocket motors, as you can imagine, it's solid rocket. I don't have a picture here for it. It's solid propellant.
Right.
Excuse me. So it doesn't require any air, right? So it is truly a rocket, right? Rocket engine anyway. So, and it usually burns about 2 to 2.5 seconds. So not really, it's not burning the whole time it's flying. It's basically accelerating up to a certain point, and then it's a ballistic, almost like a javelin.
Right.
That's going to be guided. So, and that would be obviously the engine, the solid rocket propellant anyway. Right. And I'm sorry, I'm at a loss for the manufacturer, but it's I do know it's about 2 seconds. Oh, Thiokol makes it. That's right.
Yes, that's
Thiokol
right.
makes it. Yeah. It's got the Thiokol Mark 17. Anyway, and then let's see, talking about the roller-ons. Okay, so bear with me. So now all this stuff's going on. The thing's moving along at Mach 2.5, and things that are long and skinny, if they're not careful, they can tumble. So if you were to think of shooting an arrow, and if you take the fletchings off the arrow, do you know what happens when you release it from the bow?
Oh, it just sort of wobbles and goes end over end because of the imbalance of the arrowhead, right?
Totally. Yeah. So exactly. I call it swapping ends, but basically, it goes head over tail and kind of just falls away. So that's very inherent in a lot of these. So they have fletchings, but if you wanted to have a fletching for something going Mach 2.5, it would actually probably have to be a lot bigger.
Right.
So what they did is they said, hey, well, so when we're worried about it, well, let's see, these are big enough that it won't swap ends. The tail end won't flip over to the front, but it can induce a rolling moment. And as you can imagine, for the sensor, if you start rolling it around, it's going to get dizzy, and it's not going to help with the guidance solution. So what they want to do is, as it's running down range, even though it's in a kind of a helical fashion, the cruciform, the X of the canards, if you will, and then also the tails here, stays relatively fixed with respect to the Earth. So it moves in a helical fashion, but it doesn't rotate, if that makes sense, the missile body. And the way they prevent that are these roller-ons. So they thought, hey, how can we stabilize this, the roll or the roll rate, if you will? And they thought about servos and sensors, and that requires additional electricity, and then you have to have a battery, and then it's heavier, and you have less blah, blah, blah. Anyway, so they came up with this really cool idea, and it's basically flywheels that are on the back ends. So let me go back. So now we're looking at the cruciform tail, right? So the X kind of shaped tail. And then you see these kind of different color, like a brass looking kind of fixtures. So now we're going to zoom in on this.
The tips of the roller-on. So for those of you listening, again, go to the website, but the very extreme outer rear portion of each of the rear fins.
Yeah, exactly right. The very rear portion here. Now we're going to zoom in on the rear portion. You're going to get this guy. All right. So what you have is a flywheel. It's got little notches in it, and it turns out it's pretty darn dense. So you fire the missile. What'll happen is these little notches grab. It's kind of like a water wheel.
Yeah, I can see it's going to grab the airflow, right?
Yeah, exactly right. So it's going to take a bite out of the air. The air is going to push it anyway. And I think it gets up to something like 15,000 RPM or something crazy. Yeah. And then you have gyroscopic stability.
Okay, that makes a lot of sense. Yeah.
So what happens is, so you have rotational inertia. That's one thing, but this is the gyroscopic effect. So, and this is, I'm going to confuse myself here. So basically, as it's spinning, think of, when you guys were in high school or middle school and you had the science teacher probably sit on a stool and had a big bicycle wheel in her two hands or his or her hands. Anyway, and then they spun it, right? And then you move the axis of rotation and the chair would move in a reactive fashion, like the opposite direction, right? So those torques. So what'll happen is, as this thing is flying through the air, and this flywheel spins up. It basically is the source for a gyroscopic effect. And so as the missile rotates, believe it or not, and this is a hinge here, so sorry for the listeners, but this little guy actually moves. He deflects. I'm going to show you that here. So when he deflects, he actually has a hinge point here, and this becomes, believe it or not, a mini aileron.
Right.
On
I
the
could see
tail.
that.
Yeah. So what will happen is, in this case, and bear with me here, this is obviously just a snapshot, no motion. But if we're going to say that the missile is actually traveling and it's rotating kind of picture down. So see the way my dot's moving is this whole device is trying to rotate down. What will happen is this gyroscopic effect actually pushes the aileron of sorts into the slipstream, and it creates more camber on the side of the wing that's going down. Right. So it creates lift in the opposite direction. So it helps to stabilize or counter really the flow of the roll.
So instead of trying to have any computerized control, anything like that, they establish a gyroscopic motion or moment on each of the 4 rear fins. I know they're rollerons, but for the listener, at the back of the fins.
Yeah.
And if the missile starts to roll in a given direction, the gyroscopic effect moves the aileron into that direction because of its nature, which causes lift in the opposite direction. So it's an automatic feedback loop that doesn't use any power other than some parasitic drag.
Yeah, that's exactly. Yeah, you're just inducing lift, in the opposite direction. And so it's a passive device. It requires no electricity, no sensors, no kind of input whatsoever. It doesn't require, or requires very little maintenance. It pretty much just stays locked on the wing until. What will happen is, actually in storage, this rolleron, so an aileron with a roller to it, the rolleron is actually fixed to the wing itself, the stabilizer in the back, via this latch. And this latch, as it fires, this latch opens because the air grabs the little flanges of the latch, if you will, and kind of unlatches it. And now this thing is free to rotate about the hinge point right here.
Oh, I like that. So again, you're using all of the force you've already bought, right? You've purchased this energy through the fact of the airframe moving, the airplane, the jet, the fighter jet moving through the air. Again, man, you're dead. This is an elegant solution to all of these problems.
Oh, totally, dude. I mean,
this is awesome.
Yeah, there's no power.
No, I'm geeking out on this too. This is really cool because this is
legit. And so it's stuff like this. When the Russians saw that missile that was delivered by the Chinese Communist Party, they're like, "Holy crap, dude! We never thought of that."
Right. They probably had like 4 guys from the Gulag strapped to the back of their missile, right, with like fans they could hold out in a given direction or something.
Exactly. Totally, man. So I'll tell you what, I would have loved to have talked to the MiG-17 pilot who saw a missile come at him, wedge itself into his aircraft, not blow up. Then he maintains controllability, and he gets out of the dogfight, and he goes home and lands. What a story to tell.
Dude,
you know what I'm saying?
Props to not punching out, and then bringing that home. I mean, you were on the totally wrong side of the conflict from our point of view, but still, props to you.
Yeah, props to you now, dude. Yeah, time heals all wounds, right? So,
that's right. Yeah.
Oh man. So anyway, so that's awesome. The rollerons, and so besides the seeker and the spinning filter that kind of looks like the rising sun and all that stuff, this is the other big, like, holy crap, dude, that's an awesome idea. So is the rollerons.
Cool.
All right. So anyway, so these rollerons are used on pretty much everything, all the variants up until the X.
Okay.
And then here comes the X, and specifically we'll talk about the Block 2. Right. So the Block 2 has this this cool thing called lock on after launch. So back in the old days, you know the pilot had to confirm seeker lock on prior to releasing the weapon, as you could imagine. And nowadays it can actually it has a data link, kind of like Wi-Fi. So you can launch this beast, and then not highly recommended, but it does work apparently. You can have your radar provide information via, we'll call it with data link, but via Wi-Fi, we'll say, to the missile that's already in flight, and it can go track down the guy, find him, lock onto him, and then schwack him.
Okay. And so for the listener, we're looking at some diagrams here, and what this does is gives you the opportunity to shoot way off axis, among other things, as long as you have data. Yeah. And I'm seeing here, and this is fascinating because when I was leaving surface warfare, this whole cooperative engagement concept was just in its genesis and was fascinating. So to see that we've done it not just on like from an Aegis ship to an Aegis ship to a Hawkeye to an E2C, but within, you know, an AIM-9 is fascinating because the idea that you're now, let's take the wingman concept, right? What's the wingman there for? To protect you. Well, if a wingman can see the guy you need to shoot at, and you can fire, you know, lock on after launch and launch your missile that's going to loop around behind you, pick up your wingman's data through data link and schwack the guy that's getting ready to schwack you, man, that's incredible.
So you've trundled into a fantastically gray, almost black area. So I'm gonna.
Okay.
I'm not gonna say anything else.
Yeah.
No.
We'll put the stick hard over. We'll put the stick hard over and depart this particular area.
No, yeah, exactly. No, but you're totally spot on. And when you talk about it theoretically, you are absolutely correct. And then the actual implementation is really the classified part of it. But
we will just let that be. Yeah.
Yeah. But another way to think of it too is so the limitations of the aircraft are maneuvering wise are going to be G's, right? And pretty much it's the soft pink body that's flying the plane is going to be the limitation. You know, so F-16, I think 9 G's kind of thing, 7.5 for the Rhino. But so in other words, the aircraft, when it's maneuvering, is limited to 7.5 G's or 9, respectively, for the two different, we'll call them air forces. But now this weapon, I think, can pull over 60 G's. So imagine you can't quite get your nose around because you can't maneuver the aircraft fast enough, but you can fire this guy off, finally get the radar lock that you're looking for, or have your wingman maybe talk to it. And then that thing is just arcing out there like a big dog going 60 G's to consummate the intercept. So it's a force multiplier. Yeah. And
so go ahead.
No, go ahead. What's up?
I was going to say, so armchair fighter piloting it here, which is always dangerous. Does that also mean that you now maybe don't have to make the decision to come out of your performance envelope, right? So you can pull a little harder and you're going to bleed speed and you're going to come out of your corner. You're going to come off your corner speed. Now maybe you don't have to do that because the missile can do it for you and you're still in the heart of your envelope for maneuvering for the next guy, or if this shot misses. It's all these things, right?
Yeah, you're spot on. So you're right. There are no fewer airspeed excursions required, which keeps you in your performance envelope, just like you said. Yeah, so you can let the airspeed excursions happen with the missile, which has a lot of poop. We'll say a lot of oomph, right? Yeah. To continue, and its envelope is quite bigger. Yeah, and so that's exactly right. This is a game changer, the 9X, both with seekers that we kind of glossed over, but also because it's a charge couple device, so it's no longer that spinning reticle seeker. It's now a focal plane array, kind of like a little a video camera, right? Yeah. So it's got some more wicked goodness, we'll call it, in the sensor, and then the maneuverability. As you mentioned, the launching platform doesn't have to get toward the ragged edge of its maneuvering envelope, and it can still launch this guy. And then this guy has vectored thrust. You see what I'm circling back here? Yeah. So kind of like the F-22, it's got two-dimensional. So the only thing it doesn't do, it can't roll, but it can pitch and yaw, if you will. Right. But anyway,
as we've said, we don't necessarily want it to roll.
That's correct. Yeah.
Yeah.
And anyway, so sorry, what you see here, is the tail end of the 9X. And notice that with the new aft control surfaces, if you will, the roll-arons are gone.
They're gone. Right.
All right. Yeah. So it was a great. For the first 3 decades, it was a fantastic idea, and then the speed and the performance no longer allowed, we'll say, for the roll-on. So they use different control laws now.
Right, and that's pretty cool. So it's just literally vectoring of the nozzle that takes the rocket exhaust and gives an other than thrust vector. It gives a directional vector.
Exactly right. Yeah. So you don't have to worry about the control power, we call it, of the canards nor the aft surfaces anymore, because you can literally just point the thrust vector differently. And because the thrust vector is offset from the center of gravity, you create a torque. And now you get this crazy monster torque that's going to whip that thing around something fierce.
Now, and this is just at the rear, right? There's no forward
Oh, Oh, like jets coming out the front?
Yeah, there's nothing at the front because I know that's something something they're playing with on ships is the ability to have your rotational moments at both ends of the ship because it gives you greater maneuverability.
Yeah, I am totally with you. And as best I know, correct. There are no
Right. So
reactive.
we're still just working at the rear of the missile.
Yeah, no reactive
Okay.
control
Cool.
thrusters at the front. I could be wrong, and please let the listeners, if I am wrong, please feel free to
Yeah.
write in, and we will correct that wrong there.
Sure.
So, yeah, good deal.
Nice.
All right, so basically, there you go, from stem to stern, nose to tail,
Right.
whatever you want to say. That's the AIM-9 through the different generations.
Right. And so let's see. We didn't really talk about, and I deliberately the new seeker head, other than to say, I think the analogy of it's sort of a television camera, and I know there's open source pictures out there, so you can go Google them. The missile now has an infrared or other than visible light spectrum picture of the target, and then, as we'd call it in Aegis School, PFM, pure effing magic happens within the computer system that allows the missile to say, I want to stay locked onto that picture. And then everything else happens about the same. And now the warhead's a little different too, right? It's no longer a continuous rod. It's annular blast. Is that correct?
It is, yeah, exactly right.
Okay.
So think of another death donut, but it's no metal now. It's all energetics, right? Just kind of explosions, and it's predominantly biased forward. So it's a death cone. How about a death ice cream cone? We'll call it, yeah. Instead of
so when you say that, you mean there's not an actual shrapnel component to the warhead. There
is, but it's not as great of a mass percentage. It's not as big of a part of the explosion.
Interesting. Okay. I'm fascinated by the feeling we can't talk too much about the whys and wherefores of that.
Yeah, and this one, so you're absolutely right. And for the AIM-9, because it's current tech, I can't
we'll leave it at we have some good stuff, and it does.
It does. And the Seeker 2, and then, and I didn't want to build a slide for this for maybe plausible deniability, but I know we're being recorded. So when it comes to the Seekers, though, we touched on it a little bit in the beginning, Scott. So if you don't mind, we'll just, Roger, sorry, we'll just kind of wax poetic. Yeah. And that would be on countermeasures.
Yeah, I was going to say we should talk a little bit about how you counter this.
Yeah, so it's a cat and mouse game, so the missile is good, and then the bad guys countermeasure, then the missile gets better, then more counter, back and forth. So, and it's predominantly all physics. It's not going to be necessarily logic or, reprogramming the weapon. It's going to be what does the weapon sense? How does the weapon sense it? And then how can we fool it or how can we blind it, right? So on the unclassed side, so keeping it very theoretical, the sensor can be blinded. Right. So let's say it's human eye and you're looking out and then all of a sudden the sun pops up right in front of you. You can no longer see your target because the sun's right there. Right. So it basically washes out the picture. So there are ways to do that with the Seeker, both the old Seeker and the new Seeker. They can just wash it out. So basically provide such a high intensity energy source that the weapon goes blind.
Right. Just like we would when you flashlight somebody in the eyes.
Yeah, totally. Yeah. You lose your night vision kind of thing. Yeah. And once again, on the unclassed side, so if you look at Air Force One or, the plane that carries the president and the VP and all that, they have omnidirectional, we'll call it, or I think omnidirectional, IRCM. And it's going to be this bloom. So this, so anyway, just go look online and you'll see the countermeasure.
I think you can see them on, because I've seen them personally close up on Blackhawks that I've flown on, and I believe they're on, and they sort of look like a not a disco ball, but almost a disco cylinder.
Can. It's a disco soup can. Is totally what it is. Yes, you're right. Yeah, it's a highly reflective, multifaceted canister.
Okay,
is totally what it is. Yeah, and those are focusing lenses, as you can imagine, to make that intensity quite crazy. So so you can blind it. You can also fool it, which would be flares, right?
Right.
So, and with flares, so obviously the flare is not it wouldn't be very effective if it's flew formation off the target aircraft. So it's going to fall probably away and behind, right? But, and so what happens is then you look at the characteristics of the IR emissions of the flare versus the exhaust of the aircraft. And, so you have your energy level, which is going to be directly correlated to the frequency, right? Or as we called it earlier, the color, right? Coming off it. So you got to make sure you have the correct color of the plume and the flare. And also there's rise time of flares. Have you heard of that?
I haven't.
Okay, so what'll happen is it's the actual time it takes for the flare to ignite and to achieve full brilliance, we'll call it.
Okay.
So
Yeah.
obviously the flare is sitting in the aircraft, it's not on fire. You punch it out the bottom, and then it's going to take milliseconds, but it's going to take a millisecond to achieve its final kind of operating temperature, and eventually it'll burn out too, right? So what'll happen is some of the brains on board could, and I'm being careful here, could be smart enough to figure out, oh wait, this thing is a brand new heat source, and it just popped up out of nowhere, so it must not be an engine, it must be something unnatural like a flare.
Right.
So,
okay.
So there's kind of rise time on flares is something that people can mess with to try to mess up seeker performance. Yeah. And then intensity. So it's got to be the right wavelength. It also has to be bright enough. So that's
right.
Different, mutually exclusive from frequency, or kind of the color of the light is going to be how bright it is. So
and I've heard, I haven't seen it. Well, and how would you see it? I guess, right? You'll understand why I say it.
Yeah.
I'm used to the super bright magnesium bright flares, right? And my understanding is we're moving into an era, and I'm not saying us, the U.S. specifically, or Russia, or anyone. So not looking to go gray or into a black area here. Like flares won't even be visible in our visible light spectrum potentially.
Well, yeah. So it's going to be based on the sensing strategy of the sensor itself.
Okay.
So is the sensor stronger in the IR region, the near IR, the far IR, or is it more UV?
Yeah.
Because those high energy afterburners actually give off a lot of UV too, ultraviolet, right? So you're right. They're going to tune it, the flare characteristics to the sensor kind of heart of the sensing envelope, if that makes sense.
Okay. And so, and like you said, this is the ongoing cat and mouse of action reaction. Somebody's missile gets stuck in somebody's MiG-17, and suddenly a lot of design changes can be made. And a war happens, and you capture somebody else's missiles, or you capture an airframe with someone else's flares, and now design change happens. Or the one that I think is the most despised of all military guys, someone spills the beans, right? Someone sells out to the other side, and so all these different ways it can be done.
Yeah, there are traders. I'll tell you what, though, a quick aside, then we'll jump back. So I won't go too far down the rabbit hole here, is Ukraine. So Ukraine, also the Syrian conflict with ISIL and all that stuff when it was going on earlier. Imagine having a science experiment that's a real world war, so an actual war that's fought by non-Americans. And what if we could inject our weaponry, our new weaponry, into those wars to see how they perform and not lose any American lives in the process?
Yeah.
So it is unfortunately, it's a reality for us and every other country. Is if we find a war, let's go try out our new tech in the war.
That's right.
You have to be kind of clandestine about it, so we don't.
You don't
declare war.
You don't want to start the next big war doing this.
Exactly. Yes.
And we are not implying that there are U.S. forces engaging anyone anywhere. That's not what we're saying. That's not what we're saying at all.
But theoretically speaking, that would be a great way, I think, to exercise or to experiment and test our new weapons is in a real world war. Right. So, so let's shift back to 2017 when a mob shot at the Su-22, right? The fitter. Yeah, there you go. Syrian fitter. And not him, but his weapon missed. We got a lot of good data from that.
Sure.
Because I don't know how often we had tested AIM-9Xs against Soviet inventory when it comes to flares, but anyway, I think we got some good info from that. So
and I mean, weapons are like anything else. You learn as much, if not more, from your failures.
Yes. Oh yeah, totally. Unfortunately, as a test pilot, I learned most about the systems when there was some kind of failure.
Sure. Yeah, absolutely.
I really got to dig into the books for this one. Yeah.
Nice. So. All right. So what's the future of the AIM-9? And we don't have to get technical, but what is on the horizon? Is it like, hey, AIM-9X is going to keep getting different blocks? Have they said, look, we've stretched it as far as we can, and what comes next is wholly different? Or does anyone know yet?
So I don't think anyone knows. And before we get into the employment, the man-made employment, I'm going to guess the next, not domain, but the next chapter or
Mhm.
era, we'll say, for the AIM-9 is going to be more autonomous integration.
Okay.
So just my guess. I have no
Yeah.
clue, but I'm just thinking, let's strap an AIM-9, maybe smaller because these things are not light and they're
Right.
not and they're pretty big, right? Let's strap it on a little drone and
Yeah.
have the little drone shoot down another little drone, or maybe the little drone shoots down a balloon, or I don't know, or hits a
Right.
sensor, and yeah. So
Or
I
I mean, and I'm spitballing. This is Scott Chaffee, and look at it. This stuff out there. This is nothing that Sunshine has seen anywhere. Uh, when you start talking loyal wingmen,
yes,
CCA concepts, smaller,
yes,
lighter missiles make for smaller, lighter AI-driven wingmen,
yes,
and I think warfare starts to blend after a time. Not to get too philosophical, but you know, you never wanted to fight a submarine with your ship because you're almost always going to lose if it's just ship versus submarine.
yeah,
But when the ship is the sensor platform with a towed array and you've got some helos or you've got an air asset, now you have greatly force multiplied. So I can see a world where the loyal wingman concept and you're launching off axis on a guy and you can get closer. I mean, it's going to be a game changer.
yeah. I agree. And then also target discrimination.
Okay.
So
Mhm.
what I mean by that is, let's say you have a bunch of loyal wingmen, so a bunch of drones out there, but there's one human in the mix, or one
Right.
piloted aircraft in the
Yeah.
mix. You got to be able to fire a weapon, and you can hit the drones all day, but the human, the head on the snake is still around, right?
Right.
So you'd love to cut off the head or shoot down the organic controller, whatever.
Mhm.
So I could see some target discrimination that way, whether it be offboard sensors discerning or resolving the correct
Mhm.
target and then passing the information of the weapon, or if the sensor itself on board has some kind of discrimination function, if
Yeah.
you will,
And I
or
bet there are
discriminatory.
JAGs who are going, this is an entirely new ethical concept. Could you
Oh, dude,
imagine
totally
yeah,
is. Yeah,
yeah,
so now you're talking law of armed conflict, right? Or LOAC.
yes.
Yeah, that's a whole can of worms that yeah.
Yeah, let's not even go there.
Cool. Hey, do you mind if we shift gears into a so concept of
Let's do it.
employment?
Yeah.
Awesome. Cool. All right. And then once again, my apologies for those listening. You probably want to check out the slides at home, or
Mhm.
if you're DCS fans, you may hopefully already know what I'm talking about. So, Scott, a long time ago, galaxy far, far away, we talked about how this is an elegant weapon. So it takes
Mhm.
minimal training, minimal input to provide maximum output, right?
Right. Mhm.
Yeah, cool. Sorry.
Yep.
So what you got here is how intuitive can we make this? And what I mean by intuitive is how little training is required to be able to have this air crew, this pilot, perform effectively. So there's a series of tones that we talked about earlier for lock on, and then the indications are very simple. So I kind of think of the AIM-9X here as there's three different modes of employment. One is seeker only. So you're not going to worry about your onboard radar. You're not going to use your helmet, right? Your
Mhm.
joint helmet mounted cueing system. You're just going to basically see where the seeker is. You're going to maneuver your aircraft so the seeker that's bore sighted are kind of locked straight forward. You're going to drag that seeker field of view,
Mhm.
over the target and then let it lock. If that makes
But
sense.
by brute force of maneuvering your airplane, you're just
There you
going to
go. Exactly right. Yeah.
drag the missile by virtue of it being attached to the pylon on the wing,
Yep.
or the chin station or wherever. You're just going to drag it
Sure.
around. Okay.
Yep. And you're just going to pitch your nose around and then point the target. Consequently, the weapons point the target. It locks
Mhm.
and away it goes. And the way we do that is via this little circle here. So that's our seeker circle.
Okay. So
And
nice. That's just plain circle in the center of your HUD. Okay.
yep.
Yeah.
And that plain circle in center HUD just merely represents to the pilot the instantaneous field of view. So exactly kind of snapshot what the missile sees.
Okay.
So you would just maneuver your aircraft, just like you said, to pull that seeker circle onto the target. You hear a tone rise,
Mhm.
master arm, squeeze the trigger, and hopefully it hits the target.
Nice.
So that's seeker only. Now,
Mhm.
a little upgraded version from there is going to be single target track. I know this is more of a term for the mechanically scanned radars. So we're thinking of APG 65, 71, right? Not the
Mhm.
79. But anyway, so point being, a single target track. So you have the radar out there, it locks, and then you can actually uncage. So traditionally, the seeker is going to be slaved to always look straight ahead on the missile.
Mm-hmm.
And then we have a button. It's literally called the cage uncage button. You can uncage the seeker and it'll slave to the radar track.
Okay.
So that
Yeah.
seeker's, sorry?
No, I was just going to say, so that now you don't have to continue to point at the guy, right? Now
Yeah,
the seeker's getting its cue from look where this radar's pointing.
exactly right. Yep.
Okay.
Yeah. So what you have here is you can see the box is going to be your target designator box that's generated by the radar. It's a box over the target for the folks at home that's obviously apparent in the HUD, and it's a box that's over top of the target. And that information is provided by the radar. And then inside of it, you can see the circle, and that's showing me that the seeker has slaved to or aligned to the target track, the radar target track.
Got it.
Cool. And then also, let's see, the azimuth steering circle, I believe it's called. So you can see there's a bigger circle here. That's not indicative of the seeker position. That's more representative of the kinematics of the weapon and the aircraft.
Okay.
Bear with me. So you can imagine, I know it's high off bore sight, the AIM-9, but there is some advantage, obviously, to pulling the weapon and having it launch in at least the correct direction to hit the target, right?
Right.
So that's going to be captured in very simplistic symbology in the HUD by a bigger circle. Once again, not related to the seeker, which is a little circle here. And then what will happen is there's going to be a dot. So one of your mission computers on board is going to look at where you are, look at where the target is based on radar information, and it's going to resolve it into a three-dimensional kinematic solution. So basically, how can I get a missile from here to intercept the target over there? And what'll happen is it generates this dot. So underneath my laser pointer there, dot, is a green dot. That's apparent in the HUD. And literally, instead of pulling the nose to the target, you just have to pull until this dot, which can start outside of the circle. Once it's inside of this circle, that means that you effectively are pointing in the correct direction to allow the weapon a great amount of success to hit the target.
Okay, right. So this larger circle, what was it called again?
I believe it's the azimuth steering circle.
Okay, so the azimuth steering circle, again, it's elegantly simple. If I'm hearing this right, it is a graphic representation to the pilot. Hey, put your target inside this circle, and the missile probably has enough oomph to get to it. I'm using a highly technical term there, oomph. But so almost if we go back to the football analogy, right? You were talking about leading the receiver with the quarterback. Well, now if you're a defender, if you're a cornerback watching that pass go, you need to take an angle on the receiver to tackle him. And if you're in a tail chase or all the way across the field, you might not get there. But if you've positioned yourself correctly, you have a really great chance of getting that receiver before he makes the sideline, the end zone. Sort of similar concept, right? You want to give the missile a chance to hit its target.
The best chance to hit its target. You're right.
Physically, like kinematically.
Exactly right. All that is spot on, except you don't have to necessarily put the target in the ASC and the azimuth steering circle. You have to put this green dot in the steering circle. So what happens is this green dot represents a family of curves, basically of pursuit curves, that kinematically allows the weapon to get to the target. So if the target's really close and it's crazy maneuvering, there's a chance that this dot could be in the circle, but the target could actually be outside.
Gotcha. Okay. This is probable future location of the target. Little projection there, maybe.
It looks like it from the snapshot, but it represents the amount of flight path options. It's like the heart of the envelope. How about that? So don't relate necessarily directly to the target, but it's going to look at the target. It's going to look at your aircraft, the kinematics in between, come up with a family of solutions, and then the heart of that family of solution envelope is going to be the dot.
Okay. What are the possibilities of where this could go? Okay. Got it.
Yeah, exactly. Yep. You got
cool.
it. So, okay, cool. So that would be STT, or single target track, where you use the seeker with the radar. And then finally, HOBS. This is kind of cool. So HOBS, HOB, for high off bore sight, right? So kind of a clunky acronym, but still HOBS, I guess, better than HOB. So HOBS is, and it may be hard to see in this graphic, and I'm sorry for friends at home, audio listeners here, but audio only listeners. But what you can see around inside of my circling, my lassoing, if you will, with the laser dot here,
Mhm.
is going to be the helmet mounted cueing system.
Right. And so what we're looking at is sort of the helmet mounted cueing system visor replica or corollary, because it's not a
Yeah.
replica to your
Yeah.
heads up display.
Yep. Exactly
Okay.
right. And within that heads up this, excuse me, the helmet mounted sight, you're going to see a reticle. You're going to see a circle
Mhm.
basically. And you can, instead of pulling the jet, you could just turn your head and move that circle and get the circle onto the target. So get the target inside of that circle. And then depending on if the missile physically on the wing can see the target or not, you may get a tone rise, the growl, right?
Mhm.
Or if you don't, it can fire it and then it'll still catch up to it, if that makes sense.
Right. Sort of what I alluded to that we won't go into.
Yeah. And
Yeah.
then finally, and it's not really represented well here, but believe it or not, besides the helmet mounted cueing that you can see with, that's superimposed over your right eye, I guess, we have these uplooks. Have you heard of the uplooks on the
No.
Jahimics? So we have these little flashing green lights that only be one at a time, and they're up in the very upper left and very upper right hand corners of the helmet. So think of where probably your part is, or kind of where the upper edge of your forehead anyway.
Yeah.
There's lights that they'll flash, and you can actually invoke a logic that has one of those lights flash. And if the guy is so far behind you that you can't crane your neck around to put the circle on him, just
Mhm.
put the flashing green light on him, and then there's a good chance the weapon will still shoot.
Oh wow.
Hit the guy.
Okay. So almost I don't want to say desperation or emergency, but just an extreme off-axis
Yeah.
capability.
Yep. Totally. You got it. So
Nice.
it's kind of
Okay.
high off bore sight. HHOGs.
Yeah.
Yeah.
Nice.
Yeah. So those are the three different types of employment. You got the IR only, so the seeker mode, and then the STT, which is you're adding in the radar, and then finally the Hobbs, where you're adding in the helmet.
Nice. Okay.
Yeah. So that's almost 2 hours, and
Yeah.
I'm kind of tired of hearing myself talk, but
Hey, I'm geeking out on this one, man. This is for you guys listening. Thank you for sticking with us, because I'm geeking out on this. This is fascinating. Because I really like understanding why this works the way it does and why it's so successful. So
it
yeah.
is fun. Yeah.